Hello, everybody, and welcome back to Calculus. We are now going to study section 5.6, integrals involving exponential and logarithmic functions. In fact, this will be the last section we will cover in chapter 5. After this, we will go right into chapter 6. So be ready. This is our last section on chapter 5, and we will study integrals that involve logarithmic and exponential functions. Let's get started. Okay, so let's recall one of our most important derivative formulas, ddx of ex. This is something that you will never ever forget. The derivative of e to the x is e to the x, right? You have never forgotten that. So the integral of e to the x dx is simply e to the x plus c. And I made a comment that this function, e to the x, the exponential function, and its constant multiples, those are the only functions whose derivative is itself, right? And so it is one of those unique, very unique functions. And that sort of highlights the importance of and the significance of and the uniqueness of this number e of among all of the real numbers. Okay, now we also had a sort of an associated derivative, which is a to the x. But remember, when you take a, which is not e, some base e, base a, then the derivative, you have to pay a penalty for it, and the derivative of this function is a to the x times the natural log of a, and this is the adjustment you have to make, which is pretty much essentially the penalty you would have to pay for not using the most natural base, which is e, right? Okay, so we could take the integral of this, which is what you could say a x ex. Okay, so if you take the integral of this, what do you get? Now remember, this is a constant, so this will be ax, and then the natural log of a goes in the denominator. You could do that, okay, but this is hardly ever used, so we will not have to worry too much about this. I will not ask you to use any number besides e for the base of your exponent. So this is the one that you should remember. Okay, so let's go ahead and do little exercises, a few examples using this. An easy one first. Okay, so this, now we have full use of the u substitution method, which is one of the most wonderful things. So you can do negative 2x here for u, then du is negative 2 dx, okay? And you say, well, I don't see negative 2, but that's fine, as we know. And I'm just going to put negative 2 here. How's that, okay? Because then this whole thing here is just du, right? So it's negative 1/2 integral e to the u of du, which is negative 1/2, e to the u plus c, which is negative 1/2, e to the negative 2x plus c. Okay. After a while, for something as simple as this, you probably wouldn't even have to do explicitly write down u and du. You will probably, and maybe you already are there, but if you are not, that's fine. But soon you will be able to look at this and probably go directly to this without explicitly writing u and du. Okay, so that's fine too. All right, now let me ask you a little trick question. What is this? Okay, you may be tempted to say, well, that's 1/4 e to the 4th plus c. And I can feel your problem here. And I'm a little, empathetic when you do this, because you are thinking of e as like a variable x. But remember, e to the 3rd is a constant, okay? So that is not the answer here. The answer to this question is e to the 3x plus c. So just like if I ask you to differentiate 4 as a function, integrate 4 as a function, what's the answer? It's going to be 4x plus c, right? So if this is a constant, the answer is going to be that constant times x plus c. This is a constant, so this is going to be the correct answer. So do not be deceived by what appears to be a variable. E is a constant, okay, and so is e cubed. All right, so let's do another one. X squared e to the negative 2 x third dx. Now this is a little more involved, right? So you would have to probably explicitly write down u, but again, this is not too bad because the inside function is pretty obvious. That's negative 2x cubed. Okay, let's hope this works. The u is going to have negative 6 x squared dx. Now I don't have to see negative 6, but in order to use this u substitution, I do have to have x squared dx. Do I have that? Of course I do, right? And so I need a negative 1/6 outside, and I need to have negative 6 inside, which is nice because, well, okay, I'm going to have negative 6, and I'll move this over here. All right, so I can see this whole thing right away. All right, so it's e to the negative 2x cubed, right? Again, I have not changed the problem when I do all of this, okay? I did change, I did reorder the expression inside of the integral sign. But see, this whole thing is du, right? That thing is du, and then you have the integral of e to the u. Very simple. And this is e to the u plus c. And so that's negative 1/6 e to the negative 2x third plus c. Okay. Pretty easy stuff, right? Okay, let's use this, exponential, the integral of an exponential function in an application problem. Now, e to the x, the exponential function often, and you probably have seen this before, but an exponential function often describes growth, okay? Because many things in nature grow exponentially, not just in nature, but like even in the world of finance, compound interest grows exponentially. Population, the world population seems to grow exponentially. Many things, okay? Even like the prices, the consumer price index or something, seem to go exponentially. A lot of things, if left alone, without or in the absence of any inhibiting factor, things tend to grow exponentially. All right, so here's an example. P of t is the population of flies in some sort of environment, maybe a scientific experiment or something. All right, and t is in days. And let's say we have data that says dp dt. Now, what is that? Okay. You notice here, dp dt must be the rate of change, right? So it's the rate of change of population. And so this is the rate of the population increase, is 2 times e to the negative, e to the 0.02 t. And then the, of course, you have to have units. It's flies per day. So let's say you are given somehow, maybe by data or by experiment, that dp dt, the rate of change of p, is 2 times e to the 0.02 t. Okay. You're also given that the initial value is 200. Okay. Now we have a problem very similar to this in the book, but I have changed things slightly different. Okay, so this is the situation. Okay, let's find p of 10. Okay, so that would be the population of these flies on the 10th day. Remember, you start with 200 flies, and here is the rate of change. What is the population of these flies after 10 days? Okay, so what do you do? Well, p, if you have to go from the rate to the original function p, you have to do the anti-differentiation, which is basically the integral, right? So you have to find this, and it's going to involve plus c, because that plus c is going to be indicated or be expressed or discovered in terms of the initial value. This is, again, a very typical initial value problem. All right, so I can let u be 0.02 t, then du is 0.02 dt. Okay, now I don't have that, but that's okay. Just divide this by 0.02. In fact, let's take the 2 out. Okay, and then you have e to the 0.02t times 0.02 dt. Remember, this is adjusted, countered by that 0.02 in the front. Okay, so what is that? Well, the outside number is actually 100. You can see that at 2 divided by 0.02 is essentially the same thing as 200 divided by 2, and so that's 100. And then here you have e to the u, du, and so that's 100 e to the 0.02t plus c. No problem here, right? Now, what you're given, and by the way, this is your population function. What you're also given is that p of 0, which is 100 e to the 0th power plus c is equal to 200. Now, what is that? That's 1. So you are given c plus 100 is 200, which tells you then c must be 100. Finally, now we have a complete description of the population on time t, at time t, which is after t days. And that is 100 e to the 0.02t plus 100. All right, and therefore, on the 10th day, all you have to do is to plug in this number 10 for t, and that's 100 times e to the 0.2 plus 100, and 100 times e to the 0.2, this part is going to be about, this is going to be an approximate number, 122, 14, blah, 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 plus 100. And so that's going to be 222. Roughly speaking, you're going to have 222 flies. Okay, so that's pretty simple, right? And this is pretty much all I'm going to say. Now, you're going to learn a lot more integration formulas, not just these. Okay, a lot more integration formulas in your second course in calculus, probably called Calculus 2. And so that is, something that you can look forward to. But at this point, I am going to stop this part. I am going to talk about the integrals involving logarithmic functions in the second part of this video for this section.